OpenAI released ChatGPT. We have all played with it. You can ask something and it answers, and it appears as if there is a human like capability that the system has to answer things from the knowledge it has acquired. Google has a similar chat bot called as Gemini, and it also does behave like almost like human. These are all called as large language models, and the architecture behind them is called transformer architecture. And today we are going to talk about the transformer architecture in a distilled manner. The prerequisite for this is to understand embeddings. There is a YouTube video created by me on embeddings. Uh, you may read it. In a short summary of that is that every word, or it's called token in the AI world, is represented by a vector, and that vector has some kind of meaning. So you could do vector arithmetic. So you could take a vector for king, subtract male from it, add female, and it would start becoming very close to the queen vector. So let's take an example. Let's say you have a transformer and you give it an input and it gives an output. Transformers are basically doing a sequence to sequence transformation. That means you give an input sequence of tokens and you get output sequence of tokens. The job of transformer is basically to predict the next word, and it keeps doing that continuously and you get a sequence out. So the sequence comes in, it keeps processing it, and the sequence goes out. That's a simple model. In reality, the input sequence might all be given in parallel, and the output might also turn out to be in parallel, but a simplistic way is to think about just predicting the next token. So what does transformer have inside? It has two big pieces. One is called encoder and the other one is decoder. So you have a sequence of tokens in English. Encoder takes it, processes it through multiple layers, and we could say in very simple English that it extracts the meaning out of it. And that meaning then it takes and puts it through the decoder, and through different layers, and out comes the same thing but in French. Uh, and as you would see that two words in the sequence gave you three words in the output, uh, but yeah, the meaning is preserved. What does an encoder or a decoder have? uh, Encoder and decoder again are broken into multiple layers. So when you get a hello world token, first thing you do is embedding, which basically produces a vector for each of the word, and that goes through a multiple layers of encoders, for example 6 layers, and you get the meaning, and that meaning is transferred to the decoder, and decoder goes through another 6 layers, for example, and gives you a output sequence. What does, if we go into each encoder layer, what does it have? It has two pieces, a self attention and a feed forward. Feed forward is a normal neural network which captures the non linearities, and we probably won't discuss about that much, but self attention is something that is new, that was brought into transformer architecture, and we want to talk about it. The whole idea of self attention is how can you define the meaning of each word based on the context. So the word exists in a particular sentence or a paragraph, and its meaning gets influenced by the context around it. So let's take an example. Let's say there is a sentence, he ruled the kingdom, and we're talking about the he word. The he word by itself means it's a pronoun, and it basically refers to a male. So the vector here, which refers to the male, is what his initial embeddings might point to. But we get other information, for example, from the verb ruled, which tells us that he is the king that is being referred to. And the whole idea of self attention is to use this information from ruled, move the he vector slightly towards the king uh, location, and the red is the destination we want. So in simple words, you take the he vector represented by he, add the vector represented by rule, and that these two vector additions result in a target vector, and that is the king. This is what self attention wants to do. To do this, it uses three things. Number one, it wants to find out what influence the word expects from others, and that's called query. So he is a word. He's basically about, we could say, in one way to think, one example way to think is he is a pronoun, and might be more influenced, or its meaning might be derived from verbs around it, or even adjectives, right? So here, we are, let's assume that rule is the verb which is influencing the meaning of he. So he basically says that I'm looking for a verb or an adjective around me, which will tell me more about myself. The second key piece is key, which tells how the word influences other words. So the key of rule is going to influence he, and similarly the key of the may not influence that much he and even the kingdom, but rule, let's say, influences. And value is how should the word be represented in the output. We'll go through these three things, but the idea is he tells what kind of words he is interested in, the first word, and that is query. The other words tell how they are ready to influence other words, and that's the key. You multiply query with key, and multiply means dot product here, which is basically finding similarities. So uh, key says I am the key for rule says that I am a verb, I am ready to influence noun, and this says I am a noun ready to be influenced by a verb. And when you do a dot product, it looks like they are trying to influence, this is ready to take the influence, this is ready to give the influence, and hence the query and key dot product will be a larger value. That value, when multiplied with the value provided by the word uh, rule, and so that will tell us how that much contributes to the meaning of he. And we'll go slightly more into this in a second. So here is the example, right? So we took the word he, we took it through an embedding. An embedding would produce a vector, say, of size 300, and that vector it can also be represented by a visual symbol like this, an arrow, but it is also a series of numbers, or a list of numbers. Now for that embedding, for each of these words we get query, key, and values. So there are 4 words, we get 4 queries, keys, and 4 values for each of these from their embeddings. Now we take the word he, we find out the query for the word, and we take the key values for all other words. So he itself, ruled, the kingdom, and we do a dot product of this. So we say that which query and key are similar. So this, because the word is very similar to itself, so the query and key here dot product will be big. Similarly, the query and keep dot product for ruled and he will be also big, because as we said, they are ready to influence each other. For other 2 words, the key and query dot product will be small. So we take these things, we get these numbers, dot product numbers, and we multiply it with the values that each of these words have. So we have 4 such values that we got from embeddings. Now once we multiply big with this big, you get bigger set of values here also big, and here the values become small. And then you take a weighted sum of that, which basically means that these two vectors will add on to each other, and these two may not have that much of influence. And these two vectors, when they add up, they give the output, and that output is the red arrow that we were talking, which is slightly moved uh, in the anti-clockwise direction from the initial vector we had. And that's how we have got a very specific meaning for that. So this is the mechanism of self-attention, which uses query, key, and value. Another example is, let's say somebody says apple, right? The apple word by itself is represented here, which is somewhere halfway between a apple that we can eat or apple as a company. But if somebody puts a word around it like apples and oranges, then we know that we are talking about this apple. Or if somebody puts a word around that which says mobile, then we know we are talking about Apple company. So the mobile word will work on the apple and try to push the vector towards the Apple company, and away from the apple as a fruit. So that is what self attention is doing. It is refining the meaning. So that takes us to this idea that what is meaning, and meaning is basically a vector. uh, as we said, right, encoders pass on something to the decoders, and that is an abstract meaning that they pass, and that's what produces very surprising results. So what how do we capture this meaning? When we use embeddings, typically they have 50 to 300 dimensions, but it could be larger also. As shown here, you could have 3000 elements, uh, you know 3000 dimensions. So basically what we are saying is, in the in a 3000 dimensional space, a vector is the meaning for that word, and the two vectors, whether they are similar in meaning, is found by doing a dot product. So you could also imagine this to be a sphere in the three dimension, in the 3000 dimension world, and every meaning is a point on that sphere, and the points that are closer to each other are basically having same meaning. And then we sometimes try to represent an idea or some meaning through a sentence, which is collection of words. So then the meaning there becomes a collection of such vectors in that high dimensional space. There is also this idea of thinking. Do LLMs think, or can we make machines think? It's a very debatable topic, but we can't talk about LLMs and transformers without touching on this quickly. So one basic idea is that people say that LLM is nothing but a stochastic parrot, which means it's a statistical system which has learned some numbers and is trying to, with probability, trying to give output based on that. So it's nothing but it's a parrot which has learned and is just giving back the answers. But the other way to look at it is that uh, in to do prediction, it has to do a great amount of compression, and there is a correspondence, one-to-one correspondence between compression and prediction. So the idea is that if you want to compress, let's say, dataset X using Y, the best compression would try to find patterns in Y and then use those patterns to compress dataset X. Um, to extend it, it is also said that language modeling is basically about compression. So if you can get higher and higher compression, or better and better compression, you've got a better and better language model. You are able to capture all the patterns in that compression. An idea about compression is Kolmogorov complexity, which for an object, say you have an image, you want to get to the shortest program that can produce that object as an output. So if you are able to take a 20 MB of image and produce it using 10 lines of code, then you have achieved the best compression, and that's the Kolmogorov complexity. Once you have achieved that, program is the model for the image. It's the it's the uh, representation of the image, uh, and it's the highest form of compression. So and it has found all the patterns, and that's the idea. So once you have found the patterns, you also do, we know through self reflection that we do few more things. So for example, what we do is we try to generalize, we try to create abstractions, and through this we get more and more patterns, and then we try to partially match patterns from one to another, and then import parts of it. So we have seen that different branches of mathematics, we try to import ideas from geometry into algebra, and so forth, and try to sometimes prove things using different branches of mathematics while importing ideas. So the whole idea of compression is to find patterns, and you find patterns from different parts of the world, parts of the domains, and try to find a partial match, and then also import things. Another key idea in thinking is that we generally sometimes do multi-step uh, thinking, right? So it is not that you just do one step. So for example, if somebody says, when the prime minister, when the emergency in India was put, said something, so you would first find out when was the emergency put in India, and then you will find out the prime minister at that time, and then you will try to find out what that prime minister did. So it could be a multi-step process, and we have seen when we try to prove something in mathematics or try to solve a problem, we go multiple steps. So it could involve multiple steps. But given that LLMs are able to model the language, and they are, let's assume that they're doing some kind of compression, which is basically finding the most abstract patterns through multiple layers of encoders. And we also have the fact that it is said that language is thinking. Basically, you think in a language, and language represents a way to organize thoughts, and that's why you invent new languages if you need new way of thinking. But language represents thinking. So one could say that this whole idea of finding compress patterns, compressing the information, and doing it at multiple layers, you are basically trying to find more and more abstract patterns, and then once you've found the most abstract pattern, you transfer it to the decoder, and then decoder from there starts generating the same thing in a different language. So maybe the machines are thinking, and it's just matter of creating more and more layers, and better compression, and maybe bigger and bigger vectors to capture the meaning. There is also one more new invention in the area of large language model, which is the multimodal LLMs. So the idea is that instead of just training the large language model on text, can we give it different types of inputs? So you could give it, images or videos or audios, or some animations, etc. And all those are very different from each other, but the LLM would be able to build abstractions or patterns, which are beyond just text. So it's not just about predicting the next sequence of word, but it might find patterns that are in audio or video, and then try to even relate it. And this takes us to multimodal LLMs, which are surprisingly much more human like than just LLMs. And the way you use these are similar to the other LLMs, where you basically give an input, some instruction, and you get back a response. When we use LLMs, we often have to use it in certain context for solving certain problem. And the LLM might not be trained on the data that is specific to that problem. So that data might be either domain specific, or it might be for a particular organization and hence not available, openly for LLMs to get trained. In such situations, what we do is we use retrieval augmented generation, where when the person asks a question, we try to gather more information for that question, so that we can pass all that to the LLM and get back a much better response. The way we do it is, we take the question, we have this domain specific information that we have stored in some database. Typically they are called as vector databases, and we try to search, given the question, we try to search the parts of information in that database which are very similar to the question. So again, it boils down to finding similarity. So you take the question, convert it into embeddings, then find in vector databases things that have embeddings which are closer to what is present in the question. You retrieve the text, you take the question and the text together, creates a bigger prompt, and you pass it to chat GPT. Sometimes we want the systems to do much more complex tasks, and that's where agentic AI comes in. The idea there is that we would build an agent, and that agent would have certain capabilities and some autonomous behavior where the agent can do its own planning. So let's say you want an agent to go to a website, download the pages, understand what it means, and then check in your organization policy whether that website conforms to certain expectations. So what agent has to then do is understand that, oh, I need to go and download, crawl the web and download the page. It would have a list of tools that it can use to do an action. So it picks the tool, it has to make a decision on which tool is important. It picks the tool and it does the action. Once that is done, the next thing it has to do is it has to take that information and put it in its short term memory. It has to then find out what is the next step. It has to ask LLM whether, you know if what does this website contain, right? So it will the next step would be to again pick a tool which is about connecting to an LLM, and then find its view, LLM's conclusion. So the agent here is doing multiple things. It can store information in short term and long term. It can do some kind of planning. It can be asked to reflect on its actions and chain of thoughts, and it is also doing some kind of decision making all the time. So instead of the old way of writing down the steps in the code, we do not write the program as a procedural system, but we give all the tools and let the agent, which uses LLM again behind the scenes, to make decisions on which tools to execute in which order and what to pass to each, and finally get to the complex goal of whatever the human wants. So in conclusion, we talked about transform model architecture in very simple and easy to understand terms. The real architecture looks like this, although it appears complicated, but it has very similar thing that we talked. For example, you take inputs, you put it through an embedding, then you have multiple levels of encoders, right? So you have, and each of them have attention and feed forward. This is all called as encoder, this left box. There is also this notion of positional encoding, which basically means that when you give a sequence of words, each word's position also matters, and you can't consider it to be just a bag of words. Similarly, the decoder then basically does very similar things. It basically goes through again decoders, each of which is has an attention and feed forward, and then it basically outputs you know the different words. So it's very similar with few more details. Thank you for listening. Hope you enjoyed it. Uh, I look forward to learning from your comments, and also if you have questions, feel free to add to the comments.